Alright, back to live, but I think the video I was recording just got lost. Hey, let's continue here. We still have a 20 minutes here, okay? Yeah. Okay, that's a nice short break. Okay, so based on the Euler's formula, okay, I have this identity at here, which tells that the cosine y is equal to e to the power gy plus e to the negative gy divided by 2. Okay. Now this seems to be a redundant, but again, this is actually an identity often in time we use to do some simplifications. Now similarly, if you do this operation, right? This operation is plus. Now if I do minus, we're going to get 2j sine y. So in other words, we can write the sine y as e negative gy minus e negative gy over 2j. Okay, so these two are quite important identity for based on the Euler's formula. So again, Euler's formula is this expression at here. So when you have e to the power x plus gy, and you can write this into this format at here. Okay. So basically, as you can see, your complex number can be written as here is a real number and then times and the bracket of this. So that actually should remind you of what? Should remind you the polar format. So let's say I have a complex number written in, let's consider this. Let's consider a complex number written in this polar format. So in this case, here instead of theta, I'm writing as omega t. So basically, here theta here is omega t. Now, if you look at this complex number at here, right? This is very much like the Euler's formula. So this is cosine y plus j sine y. So the theta here, you can consider that as a theta, right? So what can you write this one into? You can write it into the e to the power of a j y. So basically, for this term at here, I can write it as r times e to the power of j omega t. So from here, you can write it into this e to the power j omega t using Euler's formula. Okay. So what does this actually the complex number do, right? So let's give it a little bit of physical meaning at here. So when you have a complex number z equal to r times cosine omega t plus j sine omega t. So what does it do is you have r as a constant, right? If you plot the z, and basically the theta changes at omega t. And theta changing omega t basically means it's as if you have a rotational motion, right, for the theta. So the theta keep changing at a constant angular speed omega. So if you plug in different t's, you plot all of that out, you're gonna get a circle, right, for the z. And the z is on the circle, and it's moving at an angular speed of omega. At any location, right, you have its modulus as r, and this is omega t. Okay? Yeah. So basically, coming back to Euler's formula, if you see this thing, if you see a complex number e to the power j omega t, what comes into your mind should be, oh, I got a point actually. It's moving on a circle, right? Counterclockwise, with an angular speed of omega and here. Right, so you got basically a rotational motion. Right. So instead of writing cosine omega t plus j sine omega t, you can just write it like this. And that's actually in the future what would jump into your mind when you see e to the power of a j omega t. Or even when you see e to the power j theta. Right? So when you see e to the power j theta, then what should come into the mind is, okay, I have a complex number that has a theta angle. If I put an r at here, so the amplitude is r, and the theta here is the angle between that line and the real axis. Okay. So that's what in the future will jump in your mind. So when you have a complex number written as rej theta, then you get this. Okay. And theta can be anywhere, right? Yeah. Okay, so let's give a couple. Let's look at this ej theta here. I'm going to let theta equal to pi. Okay, and the e theta, just let theta equal to pi. So if I let the theta equal to pi, so think about this rotation, right? Think about the rotation here. So you start from theta equal to 0, and then theta will change until theta equal to pi. So pi will be here, right? So when theta equal to pi at here, let's say consider r is unit value 1. So then this ej pi, what's that going to be? -1, right? Okay. This one is one of the most elegant equation in the world. Why is it very elegant? If you look at this equation at here, what do you see? You see 5 important constants. Can you name the 5 important constants in this equation here? What are the 5 important constants? There are only one. Let me rewrite this one here, okay? So what are the 5 important constants out of this equation? Anyone? 1, yeah. What else? J. Anything else? Pi. What else? E. What else? 0. 0, 1, J, pi, E. Right? So now you don't realize how could one equation, right, relates all of the 5 seemingly unrelated constants at here. As you probably learned, pi is important, right? We all know pi is important, right? We all know E is important, and we all know J is important. We all know 0 and 1 important. But Euler's formula here relates the 5 constants in one equation. Remember, what's the special part of E and pi? E and pi are what kind of constants? They're called irrational constants. Right? Irrational constant basically means you cannot express this constant with a fraction of 2 integers. Right? So that's why it is special. And J is also special, right? So this equation, this is one of the most elegant equations actually. Realize it or not, in the history of mathematics. There are so many, because the constants here, there's so many applications of this constant. Yet, you can actually relate to the 5 constants using this one single expression, right? So that's just simply amazing. So I want you to remember this, but you don't have to remember this. I mean, you can always derive this very easily, right? Yeah. So let's take a look at a couple examples here, applications of Euler. Can you calculate what is I to the power I, or in my words, I write j to the power j, right? What is j to the power of j? Now but just look at it, it's impossible, right? What's j to the power of j? I know j to the power of 0 is 1, but I know what's j to the power of j, right? So let's use Euler's formula to do this. If I calculate e to the power of pi over 2j, I will get a j here, basically. Okay. So it's like this rotation. See, you start from 0. If you rotate 90 degrees, and you're on the imaginary axis, that's j, right? Yeah. So this one you get the j. So j basically is this guy here. So then j to the j, I can write it as e to the power of 2 pi j, and then to the power of j. Okay. So here is e to the power of a to the power of b. So it should be what? E to the power of ab. So then this term should be e to the power of pi over 2 j times j. So that together you get e to the power of negative pi over 2, which is approximately 0.208. Right, so that's an example to use Euler formula. Now you can actually calculate this j to the power of j. Right. So I want you to try this. What is j to the power of j, and then to the power of j? And what does this equal to? Yep. Okay. Yeah. Try yourself using the Euler's formula. You can get the results out of here. Okay. And the other application of Euler's formula is this. So let's say I have a complex number, z1 equal to a1 plus jb1, and then another one is a2 jb2. Okay. So let's say I have two complex numbers here, okay. And I want you to multiply z1 equal to z2, multiply z1 z2, right? Okay. So we can do the multiplication as we did in the previous examples. Okay. But now, since we learned Euler's formula now, we can actually use Euler's formula to do the multiplication in a different way. Okay. So for z1, suppose z1 has a magnitude of r1, and z1 has an argument of theta 1. Similarly, z2 has r2 as its length and angle theta 2. Okay, so basically it's like this. So you have z1 at here, and then you have z2 over here. Right, so that's z1 and the z2. So then I can write z1, okay, and z2 using the Euler's formula. So z1 magnitude is r1 and angle is theta 1. And z2 has magnitude z2, r2, and angle is theta 2. So this is alternative writing, right, using Euler's formula to write basically like a polar to Euler and then back to this original one here. So now if I multiply these two complex numbers together, I will use these two expressions to do my multiplication now. So that multiplication could be just r1, r2 and then this is e to the power of what? Theta 1 plus theta 2. And you can always transform this back to the normal complex number, and that's cosine theta 1 plus theta 2 plus j, and sine theta 1 plus theta 2. Okay. So you will get exactly the same results if you do the multiplication as the standard way, right? This is a multiplication using Euler's way. Yeah. Very similar, you can try on the division. Right? If you have a division here, it's z1 divided by z2. So that's r1 ej theta 1 divided by r2 ej theta 2. So that gives us r1 over r2 ej theta 1 minus theta 2. Okay. So those operations are much simpler or less prone to mistake when you do a typical multiplications. Right? Yeah. And this is equal to r1 over r2 cosine theta 1 minus theta 2 plus j sine theta 1 minus theta 2. Okay. Okay. So that actually basically will transition us into the next topic called phasor representation of a sinusoidal signal. As you can see here, we have a cosine and a sine, and they come out of this e to the power of j theta value, right? Yeah. So let's keep looking at the application of these Eulers here, okay? And then look at what we can do. What can we do to simplify some operations? So the next topic is phasor representation of a sinusoidal signal. Okay. When we see sinusoidal signal, so it can be cosine, it can be a sine, basically. Okay, but in this case here, mostly we're actually using cosine as an example. Okay, but you can always transform between the cosine and sine by adding a pi over 2, right? Yeah. So let's start from a general complex number. Okay. So you can always write a complex number in all of these notations. So 1, 2, 3, either one of them is fine. And to add on top of it is the fourth one. We can also write a complex number as this. So z equal to r angle theta. So you have now you have 4 different ways of writing complex number now, okay? So there are 4 ways. So good? Yeah, so all of them refer to the same complex number. Okay. So now let's look at let's say given a sinusoidal function. Let's call v of t equal to a times cosine omega t plus phi. Okay. So let's say you have a sinusoidal function given at here. And this is a very typical sinusoidal. When you are running maybe an electrical circuit, and you probably will insert the circuit with a sinusoidal curve. So this curve right here has a magnitude of a and the frequency of omega, and the phi right here, if you recall that, this is called what? The phase, right? This is the phase, and this is the frequency, and this is the magnitude. Okay, that's how you represent a sinusoidal here. Okay. Now you can manipulate the sinusoidal. Maybe you have this one plus another one, or maybe they have this one, multiple ones adding each other here. But we can now, since we learned a complex number, we learned the Euler. Okay, we actually can use the we can rewrite this signal using the Euler's formula. Okay, so this v of t. Okay, let me rewrite it. Okay. I can write it as the real part of a times e to the power of j omega t plus phi. So I can write it as this. Right? So because if I expand a times e to the power j cosine omega phi, then I will get 8 cosine this plus j sine this, right? So the real part, you get back to this. So then I can actually manipulate this in the future using this notation here. And this notation, I can rewrite it as e to the power j omega t and e to the power j phi. So this a to the power j phi, okay, according to my notation, I can write it as a angle phi. And this is called the so-called phasor, a new concept called the phasor for v of t. Okay, it's a phasor. Okay. So let me give me one illustration, and we'll call it day here. Okay. So let's illustrate. First, let's illustrate what's a phi or aej phi. Okay. So if I plot this aej phi a phi, so basically you find the phi angle, and this is at the amplitude of a. So right here is the aej phi. That's called the phasor, right? That's called the phasor. Okay. So then, what about altogether? What about this whole thing in here? Right. So this whole thing in here, if I using the same circle. Okay. So if you compare this one and this one, the difference is what? Is this one here, right? The difference is this. So when you multiply this with this, you are actually basically it's like this. You start from here and then travel up to this, that's omega t. So this value here is aej phi and then ej omega t. Right, so this is aej phi, that's ej omega t. Okay? And it's, of course, it's gonna keep rotating here. So what about v of t? If you drop this to the real axis, the component is the original sinusoidal signal, v of t. Okay, so I'm continuing it here to show you that how do we use the phasor concept to do some simplifications. Any questions so far? Okay, thank you.